Yesterday, I gave you an overall presentation of an integrated research plan that had the dimension of analysis, policy, and material development. Professor Katana. Today, I would be particularly focusing on one aspect of the research, which is the development of highly reflective durable materials. And the research would have two components, is roofing material and paving materials. And it is, there are some parts of it which I use a little bit of sophisticated math, but don't be worried about it. If you have taken any engineering mathematics, so that's nothing to be worried about. So to just kind of whet your appetite, this is the present Perugia, the older part of the city. And in addition to this, you have some area about 10 times larger than this area that is New Perugia, and it is made from all new surfaces, practically dark asphalt or dark roofing materials. And one can use new technologies in order to have them cool and at the same time keep the same appearance for the city. So for the technologies that we would be looking at, we would discuss an evolution of cool roofing technologies, starting from the most obvious and the coolest of all, white color, then going to the research toward the cool colored materials, then talking about directionally reflective materials, and also presenting a little bit of optics and retroreflective, and finally some of the materials that are still at the research stage, such as thermochromics. For the cool pavements, the technologies that I would discuss would be chip seals, asphalt colors that I would discuss what it is, white Portland cement concrete, uncoated chipping with white aggregates, and also using some dyes, cool dark dyes, in order to cover the surfaces. Just as a matter of introduction, all my lecture materials are always available, and I can leave a PDF file in here, and if you needed to contact me, I typically respond to emails of my friends within a couple of hours. I'm Hashem.Akbari at Concordia.com. That's the .ca. So we discussed yesterday the application of cool roofs, cool methods, and cool pavements, how they would have an integral effect on the energy and air quality. And I'm not going to repeat much of that. But the whole idea in here is that it is easy to show in line in here cool roofs. But if you look at the dimension coming out of this surface, that is material development, that dimension is not being shown in here. And so I would be basically focusing in here and in here. So I would be leaving all these areas alone, and particularly, if you are interested in this part, we will talk about that later on in private if you wish. So I had a discussion yesterday that typical cities in the developed areas are made of about 60% man-made surfaces. These are rooftops and pavements. pavements, color, streets, parking lots, driveways, sidewalks, and back roads, you name it. And of course, roofs are typically on top of the buildings or top of the structures. So we have carried out a lot of detailed analysis of what is known as orthophotos. Orthophotos are high digital orthophotography that are typically being taken at the resolution at the time that we were doing the studies of 10 centimeters. So you can imagine a city in the area of typically 10 kilometers by 10 kilometers, which is an average city. That is already 100 million square meter. And if you multiply that 100 million square meter by another 1,000 or another 100, in order to find out the number of pixels that you are talking about, you are talking about a typical city is made out of at least 100 billion pixels. So obviously, one cannot analyze these 100 billion pictures automatically, and you need very, very sophisticated programs which are typically in the form of pattern recognitions in order to identify these different samples. So what you would do is basically use pattern recognition devices, and then you use some kind of Monte Carlo or modified Monte Carlo approach that will select pixels from this 100 billion pixel and identify in what group it belongs. For instance, this is a roof that it is shaded with a tree. This is a piece of area that appears to be the parking lot. This is a piece of pavement that appears to be on the street. So when you put it all together, then you integrate that together, that becomes your database to work with. Obviously, as your number of samples increases, the standard deviation of the errors in calculating the specific surface area decreases. So you typically need a minimum of about 10,000 random samples to characterize the surface areas by something like about within 1% of accuracy. For instance, saying that pavements in this area are 35% of the land area. Having said all of that, still our pattern recognition systems cannot do the job of a typical eye of a human being. So then you at that time hire graduate students at 10 cents an hour and then ask them to look at these images and identify visually whether this pattern of recognition has had problem with and how you can improve the models. So what I'm showing you here is the results of 3 years work, just to give you an idea. When I say 3 years, it's 3 man or a person year work. It is not anything that it is done very easily. Then on top of this thing, a lot of these data are not available. You have to make a specific arrangements in order to make these ortho photos taken. So we have been contacting different companies that are specializing in this area. They typically run a special Learjet for us at lower elevation, and then they crisscross the urban area. In order to do that, you have to take permission from FCC. In order to do that, you have to get the permission from the Homeland Security. So it is not something very easy that you can immediately find out. Nowadays, with Google mapping and things like that also, it is a little bit easier, but if you look at this Google mapping, you cannot import this thing as a digital 4-color or 5-color picture. You can only have a 3-color picture, and trying to digitize this thing and analyze this thing is fairly inaccurate. So then the physics of this thing is now that you have come with these different surfaces, then the question is that I would like to develop a program, say for city of Los Angeles or city of San Jose, of implementing a light color surfaces. This is light color roofing and light color pavement. Now, a pavement that is installed in the streets has different ownership, different structure compared to the pavement that is installed on a parking lot. So you have to be able to identify each of these surfaces individually and the appropriate technologies that I'm going to talk about. The fundamentals of all cool technologies that the higher the solar absorbance of a surface, the higher its temperature rise above the ambient temperature. So if you have a cool, a dark surface with a typical absorptivity of about 95%, that is as much as 50 degrees Celsius warmer than the ambient air temperature. And if you have a typical white paint, that's only about 10 degrees Celsius. And again, some focused and metallic surfaces, even though they may have low absorptivity, but because of the low thermal emittance, can also be very hot. So the development or application of the technologies and documenting the potential energy savings in order to make it part of the codes and standards is one integral of the cool roof plan. So as part of this activity, we have taken several buildings that this particular building is a hospital in Davis, California, that we monitored the energy consumption of this building by instrumenting this building very heavily at different levels to have outside weather station, then to have a lot of thermographies from the roofing layer, also monitoring the energy consumption of the buildings. And then we monitor this type of building with the existing roof that they have, and also carry out some instruments such as pyrometer techniques and use standards such as E1918 to measure the reflectivity of the surface area. Then we start putting some cool roofing, and particularly in this application, a coating on the roof, and this is the thermal image of the roof. That part of the roof is covered with the cool coating, the other part is not covered, and this is clearly a visual indication that yes, the roof surface is cooler, but there is still a long way to go to say that from a cooler roof you actually save energy. How do you do that? So here is an example of the type of data analysis that we carry out. This is, we typically collect data depending on the different application at the frequency of about a minute to sometimes 15 minutes interval. So there are either instantaneous measurements in this period, or we would average it out. For some of these samples, we actually make measurements at about 60 hertz, and then average them over 15 minutes interval in order to get the average for that period. So here is the surface temperature of the roof before the cool roof is applied and after the cool roof is applied. Obviously, you see that the surface temperature has dropped. So that is an indication that we are moving in the right direction. Then you look at the measurements underneath the roof. You would find out, yes, underneath the roof, the temperature has also dropped by installing the cool roof. So in a way, you are having lower energy going to your roofing system. Then you look at the space that is being created underneath the roof. You will find out before the installation of the cool roof, the planar space under the roof was typically reaching about 120 degrees Fahrenheit, but after installing the cool roof, that number is about 90 degrees. You look at the heat flux through the roof, which is greatly shown that the heat flux has dramatically decreased by installing the cool roof. Then when you look at the electricity consumption, that's not as clear. You would find out the day in here and the day in post that they're almost identical. So the question here, yes, you have documented all this effect, but this is where I am paying the electricity bill. Where is my savings there? So at that time, you start doing a lot of statistical analysis. The statistical analysis, basically, you start looking at the energy performance of the building and developing some models of the performance of the building before installing the cool roof, and then after installing the cool roof, and then normalizing for the weather conditions of before and after. So as an example in here, the energy consumption before was 1094, the actual, the post-energy consumption is 915, but the weather condition of the post and pre are different. When you normalize it, the post-energy, the pre-energy consumption becomes post-energy consumption for the condition of the pre becomes 896 kilowatt hour a day. So you have an average of about 20 kilowatt hours a day saving in this building with a percentage of about 18% of cooling energy consumption of the building. So in a second building that we did the same thing, we find out that the savings are comparable. In a third building, this is actually the importance of showing this particular building, we will find out that the savings are in the order of about 2%. So what is different about this building than these buildings, that is as important to know how the cool roof is operating. Obviously, if you have the buildings of this type, you would find out that the cool roof is not as useful. So when you started looking at the details of this particular building, you would find out that because of a very, very large attic space, so there is about 2-meter gap between the top of the ceiling and bottom of the roof. And it is highly ventilated. So for all practical purposes, the roof or the ceiling and the roof are separated from each other. Therefore, based on this, we are putting elements in the codes and standards that for the cool roof application, energy savings may not be as much in totally ventilated buildings. So, important elements, and you need to really understand your buildings as clearly as the cases that we have in here in order to have the effective standards. I mentioned that the first approach was to start looking at the white roofs, and white roofs are widely available in many places, Mediterranean, this is Bermuda, and one of the applications of this white roof, particularly if it is calcium carbonate, is that for islands that are short in sweet water, they would be collecting rainwater and dews from the roof in the system underneath this building, and they use that as the potable water. And these technologies have been applied for the last 150 years there, fairly few development, and have been applied for thousands of years in the Mediterranean area. And this is the case in Santorini, Greece. And this is the case in Hyderabad, India. There are a lot of newer buildings when they are considering to put air conditioning in the buildings, they first think whether it's better to have a cool roof. And since the application of the cool roof, because of the cheap labor, is much, much less costly than paying for electricity or buying air conditioner, this is really mushrooming very, very fast in developing countries. So another experiment that I mentioned also briefly is a flip-flop experiment in order to document energy saving potential. A flip-flop experiment is like that you have two buildings that are almost similar, monitoring side by side. Then you would do changes in one of the building and compare it to the performance of the other building as it is not being changed. Then after that is being done, you do the same change in the second building. So you start with a relationship which is like this, then you do the change, and when you do the change, such as putting the cool roof in one of those, you would find out that the energy consumption in that particular building has dropped. Then you would do the same thing with this building, and you will find out now this same relationship goes back the way it was. So this is a very, very powerful tool of field monitoring, and it is being documented in many resources for monitoring, including ASHRAE standards, chapter 38 and chapter 42 that originally I authored it. So I also briefly discussed the implication of the heating. A lot of people believe that if a cool roof would save cooling energy use during the summer, a hot roof would also save heating energy during the winter. But that is a myth, and it is not reality, because in most places that you need heating, there is not much sun during the winter. So the effect of the albedo is not as great. In some places there is sun, but it's not as great. And then on top of that, most of the heating in buildings happen in the evening or early morning hours when there is no sun. When you account for all of these things, you would find out that winter penalties are not as much. So, as an example, days are shorter in winter, sun angle on the roof is much lower, the sky is 3 to 4 times cloudier, most heating is being done in the evening or early morning hours, and in a place such as Toronto, Montreal, for half of the heating season, the entire roof is covered with the snow. So it doesn't matter what color is underneath that. So then we moved from cool roof, which at that time was a white roof, and it is very much applicable to a flat roof and to a very high standard, lucrative and upper class housing, to something which is called as the cool color roofing material. So that was the second stage of our research, and the research was on the basis that not everybody would like white. If you want to have a cool color, what is the way to do that? And we took advantage of the spectra of the wavelength dependence of incoming solar radiation. We define color of the surfaces by the visible light of the sun that comes in between 300 to about 700 nanometers. And that is about 43% of the incoming solar radiation. And you can reflect 50% of the near infrared reflection energy and still have the same color for the surface. And that has been the basis for the cool color material. An example of these things are shown in this particular building, which is applying cool brown, and this cool brown, which is designed to be like a standard brown, its performance in the visible is the same as the standard brown, but in the near infrared, its performance becomes significantly higher. We started to develop materials for different applications, and we designed for the first time a technology which is called two-layer technologies. And I'm going to talk about the mathematics of this thing in a little while. When the sun energy or any kind of photon that comes on a surface or layer of surface, three things can happen to it. The first thing, that it will be absorbed. The second thing, it will be backscattered. And the third thing, that nothing, it goes through. When it goes through that photon, comes to the next layer of material, the same two choices are possible, and so on and so forth. Now, if you have a surface that it is dark on the surface and it is reflective underneath, when the surface radiation comes in there, a little bit of it is absorbed and that gives you the choice of the color. But most of it is going to be transferred to the next layer, and if the next layer is very reflective, it is going to be mostly reflective. This is a technology which is called two-layer technologies. We like to believe that we were one of the principals in the world that invented it. Our lawyers told us that it is not an inventable patent, but Japanese have 35 inventions on our invention which was not inventable. So it is very, very basic, and it works very, very effective, and it is being applied basically for all kinds of color technologies that right now are the basis of cool colors. And this is an example of that application, that you are applying a dark agent, which is dioxazine purple, in very, very low quantities. It looks like purple, but if the dilution increases to more than 3%, it becomes black. So this black is being applied on 4 background colors. One of them is metallic. This is a case of a cool black car. One of them is a thick white background. The other is a thin white background, and then the other on a black background. As you see, the performance of all of them, visually they are the same. In Japan, about 95% of the roofs in single families and small commercial buildings are black tiles. These black tiles are needed to be changed every 30 to 50 years. When the time comes in, by the way, these are all being used with some colorant on the surface. So the material that they use is not naturally black. They have to paint it. So rather than using the standard black material to paint the surfaces or to coat the surfaces, they would put cool materials. And then they have an option of to be a dark surface with a reflectivity of about 5%, as they are doing right now, or to have a cool black surface with a reflectivity of close to 40%. Most of our colored surfaces that we are seeing in here are typically having a reflectivity of about 25% or lower. Now, suppose that I come and show you a black surface, I say that the reflectivity of this surface is much, much higher than this color. Your eyes would not believe that. But this is the basic of the science of it. So these materials have been widely used since our research has been always in close collaboration with the industry. The materials are immediately being marketed. So you do have cool coatings, you do have tiles that are coming in cool color, you do have metallic roofing materials, and on top of that you also have cool color shingles. These group of the roofing materials are covering about 98% of all the roofing type that are being used in residential buildings. So in a way, for each end use, we have an option available that it is cool. And on top of that, the incremental cost between cool and standard, in most cases, is nothing. So therefore, this migration has been very, very easy, and it's been also very easy for us to promote codes and standards throughout the country in order to apply cool roofing materials. This is something that I discussed a little bit yesterday. So now, that part was development of the material, but a lot of science had gone below understanding these materials. So the first element of the research that we did. Now this is becoming the PhD type of research that you typically do only in the lab. We collected an assortment of all colors that were available, and we could get either from open market or get it from our industrial partners. And these were all single pigment colors, and we developed some films from each of these pigment colors, and then we characterized the performance of each one of them. Now remember that each of these things is one sample. In order to extrapolate what you understand from this sample to the other regions, you must have a very, very strong theory behind it. And in order to do that, we use a technique which is based on the Kebal-Kaman technique, and I'm going to discuss it very, very briefly. So, since the objective was to characterize the put and Hall surface, a coating is typically made a transparent medium. When we are saying transparent medium, that would mean it only absorbs something like 2 to 5% of the incoming solar radiation. It's not 100% transparent. Then you add colorant or pigment to that, and that will make your coating. So the near infrared absorbance of all of these materials are being characterized, and we basically group the buildings that have high NIR reflectance in the range of 700 to 2500 nanometer as the cool pigments. So this is the general characteristic as we formulated for the cool pigments, that cool pigments must have a strong backscattering characteristics. We are going to find out how those backscattering characteristics are going to be identified. Some cool pigments strongly scatter in the near infrared, and producing cool coating over any background would allow us to reflect the near infrared even with the cool pigment alone without moving to the next layer. Then other cool pigments nearly weakly scatter in the near infrared. If the scattering properties of the near infrared of the pigment itself is not sufficient, you need to have a white background in order to do that. So here is the way that the characterization works. You have a sample that is colorant, then you make 3 films of this. One, only the pigment itself. The other is a pigment with a white coating, very thick white coating on behind. Then the third one is a pigment with black coating behind. And then you measure and characterize their performance. So 4 solar properties are being measured. Transmittance of the free film is measured. So you know that in spectrometry, you can measure reflectance, you can measure transmittance, but you can only deduce or calculate absorptance by the Kirchhoff's law. So absorptance, you would never be able to do direct measurements. Then in some cases, when you are adding your transmittance and your back reflectance, sometimes it gives you the illusion that your surface is more than 100% reflectance. At that time, you have to understand the real map, what is going on, because in some cases, you are also measuring the interference reflectance that you have to account that correct for it. So, therefore, we measure the transmittance of the free film, reflectance of the free film, reflectance of the film over the opaque wine, reflectance of the film over opaque background. So these are the 4 measurements, and we measure from 300 nanometer to 2,500 nanometer at 5 nanometer interval. And this is an example of some of the measurements of a field that we have, that this blue one shows the transmittance. As an example, you see the transmittance in the visible range in this area is fairly small. The transmittance is fairly high in the near infrared. Then you have the free field reflectance. You have the reflectance over the black cover, and then you have the reflectance over the white background. And then the red one is calculated by taking 1 minus reflectance minus transmittance. As you see that it shows high absorptance in the visible, and of course very high absorptance in the UV area. So the method is that it is being used. It is a bulk method, which is Kowalski-Munk model. And Kowalski-Munk model is the easiest model that in a media, the light has those three choices as I mentioned, either to be a backscatter, or absorb, or to go through. And then you keep track of those things. Then when you look at that model only works within the media itself, but when it comes outside the media, you have to account for the surface reflectance and interaction properties. On top of that, all of our measurements are being done with the direct light incident on the surface. That is the way that the spectrometer works. But the Kowalski-Munk model assumes a totally diffuse light in the media. So then the next level of the problem is that how your direct light over time would transfer into diffuse light as it goes through many backscattering. So you have to follow those things. So we ended up to really be spending close to about 3 years of effort, as it is all being documented in two milestone papers in the Journal of Solar Energy Materials and Solar Cells. It is apparently two papers that are highly being used by the others. So here is a simple model that you have a thickness of a layer, and that thickness, it does have an absorption property and a scattering property, and you have a background behind it. So on a small size, when a flux of I is incident on that flux size, if it is being absorbed, it is going to be reduced by the level of 1 minus Ki. And if it is going to be backscattered, that also adds to the level of the reduction to the next level. Now, if it is backscattered, it adds to the upcoming flux. So anything that is backscattered from here, it comes to this group, and then now the light is going up, has the same options. And it can also be backscattered again, that would come to this same. So it basically becomes two-coupled differential equation, that the change of the down flux is equal to the absorption plus scattering coefficient is reduced by that amount and added by the scattering of the opposite flux. And that is true for both cases. You subject this to the boundary condition that at any flux, this should add up to the total energy incident on the back flux of the layers that you have. That's the reason that you have a white and a black background in order to do these measurements. So when you solve this problem, it becomes a hyperbole closed form solution, and this is an example of that problem. Don't be afraid of it. It is a standard calculations that anybody that has 2 years of college must be able to do that. So you basically would be able to calculate the reflectivity as a hyperbolic function, and you correlate that with the four measurements in order to get the specific of these different variables. So then this was the case when all the light is totally diffused. Now, our experiment with an spectrometer shines the surface with 100% dim light. That is a different animal than totally diffuse light. And its scattering properties would also be different, not only in the material itself, but also in the surface effect. So you need to account for this one. That is becomes rather sophisticated, but let me just give you a little bit of idea. If you have a collimated light, because of the change interface, you only have about 4% reflectance from the interface. If you have a diffuse light on the surface, 100% diffuse light on the surface, you can have as much as 60% interface reflectance. This is, by the way, one of the reasons that tree leaves and wood are highly reflective, because they can change the light very fastly with the voids that they have into diffuse light. As a result of that, the interface reflectivity of the wooden material, which is not as well defined as metallic surfaces, are so significantly higher. So I think that I probably should not spend any much more time on the modeling and start showing you after these different models and improvement how the results would be. So here is an application of the 3 steps that we have done. So we have groups of 87 samples that for one given thickness and one particular pigment, we have characterized the performance. So we take the measurements of the reflectance, transmittance, and absorptance over an entire solar spectrum. Then we develop different samples. That, by the way, this is only the sample of the free pigment itself. Then we would use this measurement plus the measurements on a white and a black background in order to identify the scattering and absorption cross-section. As an example, if you find them here on this scale, it is logarithmic. You would find out that the back scattering of the light for this particular sample is very, very low. That would mean most of the light is either absorbed, which is that's the case in here, or goes through. And when it comes to here, you would find out back scattering of this material is highly, is about 10 times larger than what it is in here. So this is an example of the cool colored material. Then at the same time, you calculate the absorption cross-section. You will find out again this particular material highly absorptive in the UV and in the visible range, and very low absorptivity in the near infrared range. Now that we have done that, this is the beauty of this model that we have developed. We apply this model to another sample with a different thickness, but the same material. And for some of you, you will see that there are 2 graphs here, but there are actually 4 graphs in here. 2 of them, the solid ones, are the measured. The dotted ones are calculated for a sample that we have not used their properties in order to calculate the scattering and cross-section properties, and see how closely they predict the performance. So this model had been the basis of another tool that we developed at LBNL when I was there, which was called PING. The PING was that having a database of the cool material, if a particular manufacturer is interested in developing the coolest material of a given visible color, the ping would be able to go smartly select the mixture of different materials from the database that would provide that given color. So it would give you a design tool for the manufacturers. So further on, we compared this performance of this model with another simple model. How many of you have heard about the Maya scattering? Good. For those who have not heard about it, is that there is a sphere, light is incident on the sphere. Maya scattering, based on the principle of physics, characterizes the performance of non-interacting light between the different particles on this sphere particle. And that is being known as the Maya scattering. When you look at the scattering coefficient from the Maya scattering, compared to the Cavalcante theory, you will find out Maya scattering does a fairly order of magnitude good job, but typically can be off by as much as order of 5 in calculation. And the reason for that is that there is interface interaction between the groups of the particles that are adjacent to each other. Not all the particles are far separated from each other. So now, how to identify cool materials versus hot materials? Here are materials being plotted, and they show near-infrared transmittance and near-infrared absorptance. You would like to have cool materials that they're near-infrared scattering is very, very high. So, as an example, you would find out the absorptance in here, the near-infrared is very high. In here, the near-infrared is very high. In here, near-infrared transmittance is high, and absorptance is also very low. So you also would like to have the very, this type of application when the transmittance is high, you can apply this one. Then if you apply this particular material on a white background, it would be highly reflective. If you apply this material on the high background, on the reflective background, it would be more absorbent. The hot pigments are those that can be avoided in cool pigment. These are typically the right side, that they have lower backscattering and high absorption. This is an example of the hot pigments. So you would find out within the group of the fluorescents, you have a lot of materials in here, and then you have one there. In the development of the cool colored materials, it is two important factors. Number one is to make sure that you would avoid using some of the things that you should not be using. As an example that I gave yesterday, if you have compared the clay reflectance, the clay that it is rich in iron oxide has a reflectivity of about 20%. The clay that it is lean in hydroxide, of iron oxide, has a reflectivity of 45%. If you have quarries available of clay for making tiles that are low in iron oxide, you would avoid that. In car industry, in order to control the level of the brightness of the coatings on the car, they always add some carbon black into it. No matter what color you see, even the whitest color that you see, they have a little bit of carbon black in it. So that little bit of carbon black increases the absorptivity of the coating significantly. So rather than using carbon black, we can use a cool black. Or not to use the carbon black at all, use another agent that is offering you the same kind of performance, but the same level of diffuse brightness rather than directional brightness, rather than by absorption. So here are some examples of the samples that are strong in backscattering. Titanium oxide, nickel titanate and chromite titanate, mixed metal oxides, cobalt, titanium, these are the bluish tone, and titanium mica, which are basically coming in various colors, and a lot of them are translucent. Those that are weak near-infrared scattering, and they need to have reflective background in order to make the coating a lot more reflective, are cobalt chromite, cobalt aluminide, and ultramarine blues. Some iron oxides have the same characteristics, and many organic pigments, and phthalo blue, and kind of corundum red. These are not backscattering, but not also absorptive in the near infrared, and as a result of that, they allow the reflective background to reflect the light. So, examples of hot pigment that we should avoid: carbon black, magmates, magnetized oxides of hyperoxides of iron, copper chromite black, iron blue, potassium iron cyanide. So these are the materials that, if one is careful, one will not use that, and automatically it would improve the performance of the system by 20 points in the reflectance without spending any dollars. This application of cool color has been expanded quite widely, and cars nowadays are working on it. I remember that before the crisis started in Detroit, I was working with Ford company in order to coming up with some cool color cars, and then at that time the CEO was changed, and they started to do cost cutting. And believe it or not, when we are doing cost cutting, everybody is important in cost cutting, but the research. And the interesting thing is that their data shows that any dollar that they invest in research gives $5 back, and they should not cut on that one. And it's actually a tool of the investment that never invests in a country or in a what they call it, a growing country that do not spend significantly on the research. So for whatever reason, some of the old countries do not believe that. This is being applied also in a lot of materials, such as the interior of the cars. Most interior of the cars, you have seen the dashboards are in dark in color, and they get extremely hot under the sun, so you can use this material. They are being also used in dyeing the jackets, leather jackets, and BMW is also marketing this thing with a small BMW on their shoulder side. Now, next step of cool color is directionally cool roofing materials. Let me tell you what has defined the orders of research. When you go to a fruit yard, the first group of fruits that you see are low-hanging fruits. You pick those. In our research, that was white. Then you would see cool color, the one that you have to do this. Then the next group is something that you would start using a ladder. So perhaps this is another group of technologies that are potentially marketable and available in the industry. And this is called cool angle shingles. People are interested in the color of the roofs because it is part of the architectural aesthetic of the roof. Now, if you see your roof in the color that you want, but sun sees it flat, you are happy, the building owner is happy. So this cool color technology, this is some examples of it. This is one particular example. This is a shingle looking from two different directions. So if you're looking at it from a street, you see this color. If you're seeing it from the sky, you see this color. So during the hot summer days when the sun is high, it would reflect a lot of that energy. So the technology is very, very easy. Is that they would use quite variation of it. They would use white reflectivity or white material as the base on the entire roof, and then they put a directional paint, like a brushing on the surface only in one direction, not coming back. So that would cover part of the areas and would make it dark from the other side. And you can actually design it by itself. You know, put a little bit of aggregates and then try to wet it from one side. Then you would find out from the direction that the brush goes, it's wet. Where in the direction that the brush is not done, it's dry. That's exactly the same based on that technology. So the material would be able to come to the market immediately. So we developed, not only work with the manufacturer to develop this type of products, we also have developed a method of how to rate these products. As one of the things that I just mentioned yesterday was, there is an organization which is called Cool Roofing Rating Materials in CRRC, in Cool Roof Rating Council, pardon me, in United States. Its objective is there to label the reflectance and emittance of the material. Now, for uniform surfaces, the reflectivity is well defined. It doesn't change much with the angle of the sun or the orientation of the surface. But for a surface that it is designed to have different reflectivity at different hours of day, how are you going to label that? And so we developed a method that presented at the CRRC about 4 months ago. The CRRC board adopted that as a rating technique. And just this morning, I happened to receive the proof of the paper from the Journal of Solmat that documents this technique of how to rate this product. Basically, the rating is a detailed analysis to find out how this particular roofing material performs on the peak condition and also on the average annual condition, and on what basis to rate that. This is another class of examples of the directionally reflective material. These are corrugated surfaces that could be shingle, could be level. On the vertical surfaces, they are in dark color. On the horizontal surfaces, they are in light color. So they are being installed on the roof. The people who are on the street, they typically see only the vertical surfaces. The surface is dark. Now, the next element of the research, which is still on the cool roofs, is the aspect of the retroreflective. This is the technologies that are being used in the back of the cars. When the light comes in, it would reflect back immediately in the direction of the source of the light and shows where the cars are. So you use the same technology inside the roofing materials, and the technologies are very, very simple. Basically, if you have a sphere, and any light coming in that sphere in a given direction, if the back side of the sphere is reflective, after 2 or 3 reflections, after 3 reflections, it is going to go in the direction of the incoming light. But that's a simple physics, and you can look at the Wikipedia, and that would show you how exactly that it is being done. So the idea is that you would mix a little bit of those transmitted bits inside the roof coatings, and that would create the retroreflective. Then the next group of the research that is going on in the field, it has been there for quite a long time, is application of thermochromic materials. That on the hot days, the color will change to lighter color. On the cold days, the color will change to a darker color. These technologies, even though appear to be interesting, at least in principle, but since most of those thermochromic materials are based on organic materials, and organic materials and organic bonds, particularly the OH bond, rapidly deteriorate under the UV sun absorption, the life of those things are very, very low. Typically, the lifetime goes for about no more than a month. If you put one of these surfaces with thermochromic, you will see the performance within the first 2 or 3 days. But if you look at it after about 1 month, it's going to all look pale. The next part of the analysis or research is going to deal with the cool pavement. Now, at this time, last night we were talking about with Professor Rossi, and I said that I can typically go very strong for 3 to 5 hours without taking any break. But I do not know how many of you are feeling sleepy at this time and you want to stand up and just kind of move for a couple of minutes before I started on that one. Can we do that?
Yes.
Okay, so let us all stand up and then just a little bit of
Fair
movement.
to do so. I usually don't make any break.
Okay, then, yeah, but it was, you know.
But I teach internally, so their attitude is different.
Okay, then, good, then, yes. So,
let's stop.
may I kindly go ahead? Good, then, perfect. Pavement. If you look at the surfaces of most urban areas, not necessarily rural areas, you will find out 2 classes of surfaces. One class is asphalt concrete, or shortly known as asphalt. Then the other one is cement concrete, that is shortly known as concrete. And these 2 industries are internal enemies of each other. And one of them, for all the surface areas that they have, it is a zero-sum game. If a pavement decides to go cement concrete, that is a loss from the asphalt concrete. And vice versa, if the pavement decides to go asphalt concrete, that's a loss for cement concrete. So you will find out that there are a lot of what I would call it counter advertisement against each other. One of them say that for the asphalt concrete, you can pour the asphalt and start driving on it in next hour. Then the next one would, you see something coming from the asphalt industry saying that the cement is being laid for 1 day and it look dry, but it is not dry. Therefore, it takes significant amount of time to make these pavements working. So, once the science is being done, eventually you will need to make decision or recommendation for the to the policymakers. At that time, you will find out most of the questions and comments are coming in this way. And this is not really science, but you have to be prepared as a person who is interested in implementing the cool technologies to understand how to respond to this situation. And I will come back to this thing in a little bit shortly. So, the paved surfaces cover a large part of urban areas. I gave you the example of older part of Perugia. That is close to 100% of the surfaces are either roofs or pavements. Basically, the amount of the vegetation in the older part of the city is very small. In the most developed urban area, you have about 60% of the surfaces, man-made surfaces, and about 35% of it is made from the pavements, and 25% of it are roofing materials. And the pavements come in quite different way. They come in at areas in the parking lot that it is temporarily being used for some application, areas that are being used for fun farms, streets, and back streets, you name it. All of these surfaces, pavements, have the characteristics that under the sun, if the sun's energy is being absorbed on them, they get heated. And I do not know whether you have tried to ever cross the street barefoot, particularly if your car is parked away from the beach on the other side of the beach and you have to cross the street, asphalt street, you wear your feet. And if there is zebra crossing and you would follow the people, you would find out that the people are actually putting their feet on the white spots because it is cooler. So that is the technology that we have completely digested internally, but we are not applying it a lot in our day-to-day practices. Asphalt or pavements, by being coupled to the earth, have the capability of storing a lot of the heat and releasing it later. As a result of that, the maximum temperature on the paved surfaces, number one, is amplitude is lower compared to a roof that may be insulated underneath. And also, it happens at the later hours of the day. So a bare surface, if you look at it, you will find out that the sun peak is at 12 noon. Then your surface maximum temperature is at 2 p.m. Your air temperature maximum as 3 p.m. So the process of the sun to surface to the air temperature have each of them a lag into that. So for most areas or in the world, you typically have the air temperature about 1 hour after the maximum surface temperature, and maximum surface temperature, depending on the absorptivity surface, about 2 hours after the solar time. And here are some examples of some measurements that we did depending on the ground storage. The higher the absorptivity or the lower the albedo of the surface, the higher the temperature. And these particular measurements are being done in 2 comparable days in 2 different areas. As you see, they more or less follow the same pattern, that for every degree or every 10-point change in the albedo or reflectivity, you have about a 5-degree Fahrenheit change in the surface temperature. This is accounting for the surface temperatures. So this was the particular measurement that we did at the given time. We do experiments with pavements, typically in the field, is a very, very expensive and difficult proposition. If the pavement belongs to somebody else, trying to get permission from them to do something is difficult. First of all, the streets, motorways, freeways are out of question all the way, because to them safety is the most important factor and they do not want to get engaged in any of this activity. So the only choices that we typically have are the parking area. And with parking area, any surfaces that are being installed, the manufacturer or the installer will give you some implicit warranty. If you try to do an experiment to that surface, for whatever reason, if their surface doesn't perform, they always find a way to blame you because they don't want to pay for it. So with all of these things, carrying out an experiment like a larger scale experiment has been very, very difficult. So on this particular day, we find out about 3 months ago that 3 months before this experiment, that they are planning to resurface this parking area. At that time, we got the permission that when they have resurfaced half of this area, let us schedule it that it will be over the weekend. So in between the weekend, we have time until they come in next Monday to finish the job. Now we have a surface that it is freshly laid asphalt and aged asphalt, and we can do a little bit of playing around in here with some of the development coatings and measuring reflectivity of materials. So on this particular example, we find out that this fresh asphalt has a reflectivity of only 5%, aged asphalt has a reflectivity of about 15%, and this particular experiment coating that we are doing have a reflectivity of 50%, and as you see, the temperature range between these is as much as 35 degrees Fahrenheit or 20 degrees Celsius temperature difference. And this amount of temperature difference is so valuable in terms of the design of the pavement that it is the first criteria in the design of the pavements. We are going to discuss that briefly. So asphalts get heated and then they get cold. With any heating and cooling, they have expansion and contraction, and this cycle of expansion and contraction produces a strain and stress. Strain and stress is the cause of the failure of material. That is as simple as it gets. Then when you add this thing with other elements such as water droplets would be penetrating your surface, and if the temperature is very low, they would freeze. With freezing, it comes expansion that creates huge amount of stresses, and that would even causes the breaks further. If you go again look at the Perugia, the center of the Perugia, you will find that a lot of surfaces of the pavements have the top layers have been peeled off or cracked off. That is mostly because of the surface cooling and ice formation of the surface. So now you have to integrate in a technology that has been trying to do things in a fast way, mix concrete, aggregate with asphalt, pour them, roll them, and then leave them to something now include the effect of the albedo. They have never thought about that. And how to get to discuss it with them, not only again you need to discuss to understand the science, but you also need to know the jokes between the different industries in order to make the connections between them. So in Japan, our colleagues have been doing some performance on limited samples on the temperature of the various level of the pavement industries that are used in Japan, and looking at their temperature over time. As you see that some materials, because of the shading that it is being created, it creates the illusion that it is cold, but most of the materials around in here, that it is dark asphalt are very hot throughout the day, and materials that are reflective are fairly cold also throughout the day. So they have conducted some experiments to document this effect. Now, the cooler pavements results in cooling of the air. This example measurement is that for those people who have carried out the surface measurements around the profile of the air, you will find out that there is a very high temperature difference in the boundary layer right above the surface. But after that, the surface temperature gradient or the air temperature gradient changes very, very slowly. As an example, you may see a temperature gradient of about 15 degrees Celsius within the first half a centimeter, but the next 45 centimeter would only show 2 degrees Celsius. temperature difference. So it is very, very highly skewed profile toward the surface. So the first thing that we are basically conveying the message to the policymakers and decision makers that we do not want to make our paved surfaces in white color. Nobody likes that. All we are suggesting is that to have paved surfaces rather than having a reflectivity of 5%, to have a reflectivity of 30%. That technology exists today. People are using it on every concrete roads that you are driving. Chances are that if that concrete is low in carbon ash, it is going to have a reflectivity of about 35%. And it doesn't have any problem, and one can utilize it. Then the next step is that, would that affect the air temperature? In order to have a measurable effect at 0.5 meter elevation on a surface, you have to modify a surface of about 1 kilometer square. So this is huge problem to design as a field experiment. Can you ever think, how can I change the albedo of 1 kilometer square? First of all, can I find a parking lot that is 1 kilometer square? No. Can I find a piece of desert that is 1 kilometer square? The answer is yes. Okay. Now that you have found that piece of desert that's 1 kilometer square, suppose that you want to coat this thing with white color and carry out some measurements. How would you do that? What is the cheapest way to do that? The cheapest way, obviously, is to mix some chalk into the water and spray it on the ground. That's very, very inexpensive. Chalk comes in at about the cost of about 30 cents a kilogram. You do some estimation of how much it wants to do it for 1 kilometer, and then you say, okay, I would rent a spraying truck to do that. I put some instrumentation to do that. When you do the calculations and estimate of the cost, this is already an experiment in the order of $5 million. The cheapest possible way to do that. I have not even accounted for the fact that you need to probably have 10 weather stations in 10 different locations in order to measure the air temperature, the velocity profile. Then the other way that we would do it, let us see that I would take advantage of the natural settings throughout the world, such as the salt beds. In salt beds, if you look at it, there are some areas that are salt, highly reflective, versus dark all around them. And again, when you want to do that, you would find out that there are other issues, such as most of the salts are typically wet, and you have to separate the effect of the albedo and reflectivity together. So all of these things said, carrying out a field measurement is extremely expensive and difficult. So we have to rely on simulations. Our simulation basically shows that if you increase the albedo of the surfaces by about 0.25 in a large area, you would be able to decrease the air temperature by about 1 degree Fahrenheit. Now, the simulations that we have done is for the many cities, and this is an example of the Southern California. You would find out that if you do surface albedo and tree, you would find out the surface temperature decreases by as much as about 5 degrees Celsius, and that has significant effect on the ozone formation. And you would be able to document and propose that measure to your policymakers. So we have carried out a lot of experiments to document the potential benefits of the cool pavement. And these are the things that we have been documented, and they are very acceptable. Reflective pavements lower the air temperature of the cities. Simulations have shown that. Nobody would argue against it. Cooler air temperature saves energy and reduces the smog. In the city of Los Angeles, we have done an analysis. There were 2 couples, a husband and wife, by the name of Hall and Hall. These are economists who have carried out in 1988 an analysis for the cost of the air quality to the citizen of the Los Angeles greater area. And they have estimated that to be about $10 billion a year. Where is that estimate coming in? This is people losing work, people getting sick, having to go to the hospital, and the industry would not be able to produce as much. Trees dying and you have to replace them. Materials are being destroyed and you have to replace them more often. When the costs are being put together, within, of course, some degree of uncertainty, is about $10 billion a year. Out of that $10 billion a year, the cost of the smog is $3 billion a year. Our analysis showed that we would be able to reduce the concentration of the smoggy days or the smog exposure to human being by about 12%. So we assume, that's a big assumption, that everything works linearly. So we assume that if we reduce the smog exposure by 12%, we would save that 12% of that $3 billion cost. It may be much, much higher, it may be much, much lower. We do not have any ways to check that. So we have documented that effect. Now, the next thing is that people would say that how can you have a cool pavement for the entire layer? And our answer to them had been that if you look at the way that asphalts are being installed, you put first the first layer, then on top of that you put the coarse layer, then on top of that you put the fine top layer. We are not going to modify everything throughout the thickness, we are only going to modify the top layer. And that modified top layer is going to use the existing technologies that doesn't incur any incremental cost. So we have had some benefits on that. Now, this is something that we have been trying, everybody knows about, but we have been trying to document some data to show that a cooler pavement lasts longer. In the lab, for any isolated measure, we are demonstrating it. But when it comes into the field, and all those different components are added together, we cannot demonstrate it. And also we cannot demonstrate it statistically to the large samples that the policymakers that make their policy decision based on the input of the competing industries come up with a final deterministic answer. They are always afraid to be sued by one industry, and that particularly the asphalt industry has a very, very deep pocket. Then they would really outdraw you from all of your energy. So this is something that we have been promoting, everybody knows about it, but finding hard data to prove that it is not there. Higher reflectivity also improves visibility without glare. That in a lot of areas throughout the country, particularly in the urban area, the paved surfaces, either to be parking lots, to be the street, they are being left in order to increase the reflectivity, the visibility on the road during the night. That would save life, reduces accident, and so on and so forth. We have clearly demonstrated that the white-collar pavement or more reflective pavement would objects would be more visible. Therefore, if you want to have the same visibility on a dark pavement and a black pavement, we can reduce the level of the lighting on the white pavement or the light color pavement, and through that we can save energy. So this is also something that we have been focusing on. Now, the first important factor that it is being documented in pavement industry is that pavement distresses are highly temperature dependent, and I'm going to show some effects of that. And if one uses cool pavement, these pavement stresses can be significantly lower. Visibility are directly related to the reflectivity of the surfaces in the visible range, and there will be net saving energy. Some other people also say that, how about glare? If you have reflective surfaces, it creates glare and creates more accident. We have been saying that again in the form of the anecdotal way, that the reflectance difference that we are talking is that of an aged asphalt versus the aged concrete. How many of you have complained driving on an aged concrete road because of the glare? Practically not. So we always have been able to say that in a very conclusive manner so that the policymakers can make decisions very fast. So here is a way that asphalt pavement is being designed. And the performance grade of the asphalt is listed there, and this is talking about what type of different grades asphalt you can lay down there. Look at the next two entries of the asphalt design. The first thing is that average 7-day maximum temperature. So that is on top of the list of the design. And 64, 58, 52, 46, maximum temperature. So just looking at this thing, a cool pavement would can easily bring you material from this to this. Therefore, one can use lower grade asphalt for the same stress performance. So this group of asphalt in general are about 30% cheaper per the square meter of the top surface versus this group. And then the next thing is that maximum pavement design temperature that you would design not only based on the average, but also on the maximum itself. Is that minimum or maximum? I think that minimum, correct. It's also the minimum temperature. So maximum temperature, minimum temperature. So why are these things are important? The maximum temperature affects the viscosity of the asphalt material, which is binding material. The minimum temperature defines the range of the temperature fluctuation throughout the season or throughout the day that the asphalt has to go. So it's talking about thermal fatigue. And each of these things are a complete cycle of the stress, distress, stress, distress, and think about the rubber band that we are constantly opening and closing. After a time, they are going to fade. So that is the first design of it. So we have been talking to the Strategic Highway Research Program, SHRP, in order to include the effect of the reflectivity as part of the design condition. So rather than having one entry here, this would be surface temperature with light color, surface temperature with dark color. And we have had some degree of success on that. So here is an example of the effect on the constant stress because of the rolling effect. This is called rolling depths, and I mentioned that yesterday that this particular experiment simulates the effect on a bus stop. Consider that the area of asphalt under bus stop. Bus stops to pick up passengers and rolls. Bus stops to pick up passengers and rolls. So you are constantly pushing forward the asphalt and then moving away from it. So this kind of motion is being done in the lab, and that is being used as a rod test, which showed that using a 25% or 25 basis point increase in the reflectivity of the surface can easily increase or decrease the surface temperature by about 15 degrees Celsius. So it can bring you from this level easily to this level. So if your surface was going to operate at 50 degrees Celsius, it would fail for this condition after about 18,000 cycle of the repetition. But if your sample is 10 degrees Celsius lower temperature, this has gone through a cycle of as much as 180,000 cycles. The difference is about 10 times, and it has still not failed because of this effect. Now, remember that this is not the only way that the asphalt fails. There are many other ways, and one has to also be worried about it. This is the permanent shear strength. And again, for some of the material science people, that when you are working on the stress-strain curve, there are two ranges. One range is elastic range, that you exactly go on a linear path of a stress-strain. You increasing the strain, you go on that path, and then releasing the strain, you come up on a path. Then there is a part that is plastic. That is a slight change, permanent change in the physics or structure of your material. Therefore, when you go from the elastic to the plastic, you do not follow the same path on coming back. And that hysteresis effect is one of the major causes of the pavements. And again, you would find out in here that at high temperature versus low temperature, there is such as dramatic effect. So if you have a 60 degrees Celsius asphalt or 50 degrees Celsius asphalt, then you have permanent shear strength after about 10,000 shear repetition of about this much. And at 40 degrees Celsius, you only have about half of that in 50,000 or 45,000 cycles. So it performs better there too. The next one is the viscosity of the asphalt cell, so that the asphalt would not be brittle, and it does have some sense of flexibility that when the load changes, it would not crack. So you would find out that again, with different weather periods, the higher the temperature, the higher the viscosity, and in this case particularly, and remember that this is the logarithmic scale, the material would fail a lot faster. Visibility, we developed a model that looked at the amount of the light incident on a person as a function of artificial light from the source versus the reflectivity of the surface. And in this way, we find out that for the same level of the visibility, you can reduce the light in here by about 10 to 15% on a surface which has a reflectivity of 35% versus a surface which has a reflectivity of 10%. So this is, if you're having a street light, this is a direct energy savings potential possible. Now, this is some basic science of it, trying to understand. You should also remember that at one time, people asked us, what is your profession? And I ended up to basically admitting that I am a petty economist. I would like to add cents and dollars and suggest how to use these simple cents and dollars to the people for the decision-making processes. And this is exactly what it is happening. The science is one part of it, but actually making that cents and dollars in the real field are important. So there are all these different surfaces that you have. You have roads and streets. At this time, we are only talking about the surfaces. We are not talking about the people who have jurisdiction on these surfaces. You have parking lots, you have driveways, you have sidewalks, you have patios. But if you look at each of these things, the sidewalks, depending on where you are, typically is managed by the neighborhood or local municipality. The driveways are managed by the building owners, so are the patios. Parking lots, they are typically owned and operated either by the private businesses or by municipalities. Roads and streets are a function of are owned by the cities. They are owned by the country as a whole, as a national or federal government, or the state, depending who is, how the country is being designed for the maintenance and installation. Now, what are the materials available for this? You have the asphalt concrete, you have the cement concrete. So as an example, when you are pouring a patio, you can have a patio which is made from asphalt concrete or a cement concrete. You have chip seals that I'm going to discuss what chip seal is. You have white topping. You have grass surfaces that you can use as a part of the paved surfaces in a natural setting. You have resin surfaces. These are surfaces that are slightly underperforming, and in order for you to make it binding and performing, some of the aggregates are coming loose. You pour during the night some level of resins on that and make those perform there. You have coatings, which is more or less the same as resin, but these coatings are a lot of an asphalt basis. And you have gravels that are being used as technologies. Yeah, here is two examples of the asphalt concrete, which is shortly known as asphalt, versus cement concrete. So the technologies that are being used for the cement concrete, it is a wet technology. For the asphalt concrete, it is a dry technology. Wet technology typically requires time to water evaporate and the chemical process is happening. Dry technologies only need time for cooling down, so the viscosity comes down to a lower level, so it is safe to walk on it. So it is a different application or process toward installing surfaces. And the pavements, as I mentioned, go to a wide range of areas, and one area that I did not mention before was the airport runways and the school playgrounds. This particular slide that I have summarizes practically all the existing technologies. This is a chip seal technology. I'm going to talk about this as cool pavement technology. This is a white topping technology. I have made this joke over 100 times by now. One of the reasons that white topping technology is expensive because it takes a lot of labor. It would require 10 people, one working, 9 people looking at it. So having to pay to all of these people, it would make it very expensive, but that's only a joke. Then you do have cool coatings. These technologies are being applied a lot, particularly in the area that trucks come in order to get loaded. When the trucks come in, they typically have some permanent changes on the surfaces. In addition to that, they may have some leaks, and over time, this surface has to be rejuvenated to this surface. Then you have technologies which is known as grasscrete. rather than having pavements only from the solid pavers, you have pavements that have some porous areas that vegetation can grow out of it. This is known as grass creep. You have, this is particularly an application of grass creep in Japan. You have porous pavements. Porous pavements are particularly important in the area that you have a high degree of precipitation over a short time. In the natural setting, the ground can absorb significant part of that moisture. In a paved setting, all that would lead to surface water. Surface water would run and create flood throughout the cities, and you all remember some of these floods recently in many cities throughout the world, and the most important one was in Denver last year, that after about 24 hours of fairly heavy, but not extremely heavy rain, the entire city was flooded. Water cannot penetrate and find its way. They all find their ways toward the manholes. Surfaces are typically not very clean. They are covered with some debris. All these debris are being washed away to these manholes. When there is enough of this thing, they block the way. When they block the water, they do not allow the water to penetrate through, and then the water surface will come out. That's known as the city flooding. And of course, you do have colored surfaces that are being used as decorative ways in order to. The simplest one is the zebra crossing, which is black and white, but they are also being used in identifying some pathways. Follow the green area in order to get to there, follow the red area in order to get to point X. So let us first talk about the range of the reflectivity. For an asphalt concrete, the range of reflectivity, depending on the age of the reflectivity of the asphalt, is about 5 to 16%. As the asphalt age, the top layer of the asphalt would rub away from the granules, from the aggregates, and the aggregates show. So the ultimate reflectivity of the surface depends on what is the reflectivity of the aggregates. So, and of course, if you have highly absorptive aggregate, that reflectivity will be lower. If you have highly reflective aggregate, you can have it higher. So if you have a quarry that it is readily available and it performs well in terms of their mechanical performance, the cheapest way to use it, rather than using dark aggregate, you use light aggregate. For about 3 months, the surface is going to be dark, but after enough cars have passed by it, the surface is going to roll out, and then it's going to be lighter color. This is not the best you can do, but that is the thing that you can do right now without incurring any cost or anything. The second thing is actually a chip seal, which is a modification of this one. So a chip seal, rather than mixing the asphalt with aggregates, it will pour a layer of asphalt, which is the binding agent first, and then it sprays on top of that the aggregates. Then a truck comes in and rolls in this aggregate on the bed binder. So from the get-go, you do not have any asphalt showing. Therefore, you will be having a very highly reflective pavement to begin with. It does have its process, it does have minuses, since the asphalt is only being, the aggregate is only being pulled from the bottom. They are very resistive toward the press, but they are loose toward rotation. So if you use that kind of technology on a cul-de-sac, that the cars have to constantly roll their wheels, the aggregates are going to come loose. So it does have its limitations. Then the next one is basically using Portland cement concrete. With that, it comes the issue of the installation, timing of it, and also the cost of it. The concrete pavement are typically being designed for 20 to 30 years. An asphalt pavement, the top there is being designed for about 7 to 10 years. The cost of the concrete is typically about twice the cost of the asphalt pavement, but the levelized cost, depending on whose report you are looking at, is comparable or even sometimes lower. So if you start a gypsum with highly reflective aggregate, not highly reflective, modestly reflective aggregate, over time it's going to get dirty. If you start an asphalt with the same aggregate, the pavement is going to start getting brighter, and they all finally reach that same level of the reflectance of the aggregate. This is some measured data that we have for, I think that East Bay area. This is an area of about 100 measurements that we did in year 2000 throughout the East Bay area, San Francisco area, that measured the reflectivity of the surfaces, measured the aggregate, and at the same time got from the county the years, age of the pavement. And typically for most asphalt, after about 10 years, you start a fresh layer of the top asphalt to begin with. Again, the same data, when you look at the range of the albedo, this is for cement concrete, you would find out that the range of albedo goes from 20% to 36%. For the asphalt, it was going from 5% to about 12%. For the cement concrete in the same area, goes from 20% to 35%. So suppose that you would be interested in a forecast in here versus a forecast in here. So you will find out you are substituting the 12% with 26-28% range. It is a reflectivity increase on the average for these paved surfaces at about 15% with the current technologies. Now remember that these concretes are also not a specific, what I call it, low ash concrete. You can have concrete that are low ash that start higher, and then at the end, final edge would be about 30-35 reflectance. One other issue with the concrete is that concrete, because of being porous and water-based material, it does have provide the opportunity for more than algae to grow on that. So dealing with that over time, particularly mixing some algae resistance material in the concrete mix, is very important in the design of the concrete. So here is two pavements next to each other, newly installed asphalt versus the aged asphalt of the same material. This is two concrete, newly installed concrete versus aged concrete. As you see, there is a lot of growth on these surfaces. So we did some lab experiment that we varied three properties, the properties of the concrete, properties of the sand, and the choices of the reflectivity of them. And we measure the performance after they have set for about a 6 period of time. You all know that concrete typically gets dry within the first 24 hours. About 80% of the chemical processes happen within the first 6 weeks, but there are still some chemical processes going on after 30 years that make the concrete stronger over time. So that's one of the beauties of concrete to begin with, and particularly that is applied in the dam technology. So the chip seal is like this, that you install a binding. Then you have aggregates on top of that, you spray it, and then you roll it. And then after rolling, cars would start going up, there would be more pressing, and your surface would get looking smooth. And here the way that it is being done, and this is currently the technology is being used in about 50 municipalities in the United States. The cost of this technology is about, I understand, only 50% of the cost of pouring asphalt on the surface. So there are 4 trucks involved, sometimes 3 trucks. The first truck comes and pours in or sprays in the binder. The second truck is spraying aggregates on the surface. Then the third truck has 2 parts to it. One is rolling in these aggregates into the surface, and the other part of it does a very strong suction vacuum that vacuums all the loose aggregates. So this process happens in a period, typically it goes like this, with this speed movements. You cover the surfaces with this speed. So think about the way that I walk. By this speed I can walk about 3 kilometers an hour. So you can rejuvenate the surface of a 1 kilometer road in about an hour at most. Considering the cost of the labor, the cost of the equipment, this is really, really a breakthrough in the application of the cool pavements, because then you will be able to save 50% of your cost, and as a result of that, you would be able to maintain your surfaces more frequently if they're needed. How many of you have noted that when the winter comes in, there are so many potholes on your streets? And how many of you have complained that potholes are there forever? Nobody ever will fix this thing. So by this way, politicians can make the street more appealing. So here is, and again, an exact application of the chip seal technology. This is chip seal, this is asphalt, and this is a very bright chip seal that is applied. So basically, you can have this one versus this at no incremental cost, or perhaps 20% lower cost. One has to understand that aspects of the petty economy in order to communicate well with the policy and decision makers. If you go to Los Angeles Zoo, you would find out that they use colored or pigmented concrete quite widely in their design of the entrance of the zoo. Again, it is very nicely appealing. This is kind of a decorative application. Obviously, no much traffic is going except foot traffic on this thing. One would not recommend the same technologies all over the paved surfaces, but this is again a component of technologies to remember. The white coating that I mentioned is that typically is being applied in the areas that routing happens very fast. It is about a layer of 2 to 4 inches of the concrete replacing a part of the asphalt, and that concrete will offer a much better environment for the routing applications. So you would find out these kind of technologies exist on all the crossroads of the busy streets. Remember that there are traffic lights? Cars come in, have to stop by the traffic light, and then they leave. If you look at most busy cities, you would find out that white toppings are being used all along the corners. Coatings. This is actually fascinating, and I'm actually very surprised that this application is not as highly as I expected it to be. This coating looks very grayish, but has a reflectivity of over 50%. And this is exactly one of those examples that the manufacturer are doing things right by accident. So rather than having charcoal or black carbon as the black agent in this gray coating, they are using some other dark agent that it is readily available in the nature. So rather than this surface had a reflectivity of 20%, if they had used carbon black, using a cool black, this surface has a reflectivity of about 50%. The performance of this surface, if you look at it, then it is highly reflective, not only in the visible, the early part of the visible, it is absorbing, that's the reason that it's getting gray, but when it comes toward the red and the near red, the reflectivity is as much as about 70%. And the cost of it is only about 70 cents a meter square. This is not installed cost, this is cost without labor. Typically, you would multiply this thing for small projects by 3 to account for the labor cost, and by 2 for large projects. So if you account for a small project, this is rejuvenating your surface at the cost of $2 per meter square. Comparing this thing with pouring a free concrete layer, which would be costing about minimum $20 a square meter, this is no-brainer. And one should really use this thing a lot more. Obviously, one has to increase the mechanical performance of this pavement a little bit better to make sure that when the cars are constantly driving on this thing, it doesn't create rolling ski and it does have enough friction. But still the technology and the fundamental of it is available, and these are actually real costs that one has to consider. A slurry seed is a lot of asphalt because of the high temperature, the volatile part of it evaporates, and what is left is a brittle part, and as that result of that, when the cars go this thing, it is brittle, it creates shocks and loosens the aggregates. We have all seen that, there's no question. So the question here is that these aggregates over time migrate to the sidewalks, to the site, and take the strength from the roadways. So one way to perform this to make sure that they would kind of be fixed in bed again, to cover them with some slurry seeds. A slurry seed is a mixture of asphalt and water, that it is like a mayonnaise component, that there are really fine grains of asphalt mixed in water. When they are poured on the surface, the water would evaporate and the grains or the molecules of asphalt would bind each other and make the surface hard. Okay? So rather than using black asphalt in here, one would use this one. This is more or less the same cost as this one, but this one has a reflectivity of 50%, and this one has reflectivity of only 5%. So that's one technology to think about. I've already discussed a little bit about using colored pavements. I have seen quite a few of these throughout the different places in the world, that in some neighborhoods they use these pigmented pavers in order to improve the static quality of their neighborhoods. And again, they can use the same thing in here. One other ways that this thing is applied, you all have noted that when the tennis is being played on asphalt court is green. And the seats for the audience is all around the asphalt court, so air cannot come in and remove the heat. So what would happen is that it creates an environment of close to 40 degrees Celsius when outside is only 25 degrees Celsius on the players. So we have been in contact with the different stadiums in the world that they should be using cool colored materials for their courts rather than the dark materials on the court, because it improves the thermal environment on the players. Grass greens, again, lend themselves in the area that has the following. Number one, there is plenty of water because of the rain that we get anyway. And you set up a layer of the support, and in between that layer of support, you have areas that have collect dirt and green can grow on those. As an example, the parking lot in Miami Football Stadium is made from grass greens. The people who are going there, they go there only once a week to watch a game, and for the remainder of the time, they are not there. So basically, this performs very well, and there is enough of a precipitations in Miami that they do not have to be worried about watering them. And that same technologies, again, it's being applied in front of many offices in Japan. Previous pavements, I've already discussed this thing. In asphalt, they have a mix of fine grade aggregates and coarse grade aggregates in order to make sure that all the holes are filled, and therefore water penetration through the asphalt is very low. Now, if you select all of your grains of asphalt, of your aggregates to be the same size, it creates voids in between them. So with that, we can easily create porous asphalt. Then with porous asphalt, water can go through it and go to the underneath the asphalt. If you have enough of the storage underneath the asphalt, it would be able to gradually penetrate from there rather than creating floods throughout the city. This technology applies not only to the asphalt, it also applies to the cement concrete too. Cost of permeable surfaces, it depends on different applications that are there, but for most applications it is under $2 to $3 per square foot. And when you compare this thing with the cost of the typical asphalt, the incremental cost is fairly very small. It's very more or less the same. Grass pavers, this is again a technology that lends itself very well for the historical areas of a city. That you have, so looking at downtown Rome, you have a lot of pavement that they have these kind of stones. Of course, rather than being a stone, you can have it from concrete or a stone simulated concrete. And you can use these with some level of reflectivity or some layer of coating on the top that would not only simulate the current color in the city, but at the same time it offers you higher reflectivity. So this is a technology that we have been focusing on the research component of it and trying to have some success with with different policymakers to implement that. And on the other hand, we are facing, this is a kind of a tragedy in the science, with misinformation that goes out. As a recent report by some of quote-unquote researchers from Arizona State University has come in and said nothing but bad mouthing like color technologies. The reason is that the asphalt industry has felt threatened by the fact that many municipalities, government throughout the world and throughout the United States of adopting heat island mitigation measures, cool pavements are one of the requirements. Now, this report, which is of course an internal report paid by the Asphalt Association industry, and when I called the author of the report and I told the author, why did you write this thing this way and you didn't write it this way because this is wrong? He said that he initially wrote it this way, but the asphalt industry changed it to this way because it was more to the benefits. Let me just give you one example. The reflective surfaces, they reflect in the visible and the near infrared, but they are highly absorptive in the UV. You use actually titanium dioxide as the element to protect asphalt. Now, in their report, they say that increasing the reflectivity increase the UV reflectance of radiation, and all that UV reflected would be absorbed by the people and animals and trees and kills them. Now, that is nothing but pure garbage. And the cost of that report, by the way, was $50,000 to asphalt industry. Sorry to say that, but some of us at some times in our life act like prostitutes. And for $50,000, these colleagues have sold themselves, their souls, their reputation. So in their report, which is about 10 pages, they have something like, at the minimum, the gross mistakes of about 140 gross mistakes. That they knew the answer is not this, but they wrote it the way that the answer could be that way. And when the reporter was asking me about this particular report, I remembered that of a book, two books that was written in 1848. How many of you have read the book of the Philosophy of Poverty by Prada? This was a socialist in France that in 1948, in January, a book came in by this person, and he was trying to rationalize that you must have poverty in the society, otherwise the society would not exist. And 4 months later, another book came in and only changed the order of the title. So the first book was The Philosophy of Poverty. The second book was Poverty of Philosophy. How many of you know who authored that one? Karl Marx authored that one. And basically crushed that person in terms of presenting his philosophy. And when you look at the Google, you would find out more than 5,000 people have read, 5,000 times people have read The Poverty of Philosophy rather than Philosophy of Poverty. So when I was talking to this reporter, I said that the only thing comparison that they can compare is really that these people, for $50,000, they are trying to provide that kind of misinformation. So governments are becoming more aware of this thing, But at the same time, you have industries that are fighting it with misinformation, anecdotes to combat that because they are afraid of it. Then you also find out a lot of academia throughout the world that are doing research in this area. When we started this research 30 years ago, in more or less 1984, one lab, LBNL, was the only lab doing work exactly with this name. Other labs throughout the world were doing research in this area, there's no question on that. But with this umbrella, that was the only lab. Nowadays, we do have close to at least 100 labs that I know of that are focusing on all of these aspects that we discussed. So, science finds its way through, but still we have a long way to go from the science to the government and installation. So, as we did it in 14th century, coming out of the Dark Ages, this is dark surfaces. We are also in the migration of coming from that Dark Ages by applying some of the existing technologies, chip seal, coating, white PVC, antique PVC, and also doing some experimental coatings throughout the world. That basically concludes my comments on these cool surface technologies. And again, for those of you who were not in here yesterday, I would like to let you know that there is a conference in Perugia in October 13 through 15, that Professor Rossi is one of the coordinating members of the organizing committee, and we have already got over 200 abstracts, and we were hoping to have an all-inclusive small gathering, but it looks like now we are looking at a minimum of 300 people there, so our way of organizing it to there is just to try to get more help from the different people to help us organize. And so with that, I would like to conclude my comments, and if there is any particular questions, you guys have been awfully silent. And this is not supposed to be only a lecture, but kind of discussions. Thank you for attention and questions.